Welcome back. So, till now we were interested in understanding various quantities associated with the transfer function, both in in the continuous domain as well as in discrete time domain, and its effect on the dynamical behavior. When we said the dynamical behavior, we were basically focusing on the rate of response or the speed of response. One important characteristics of dynamical feature is the stability of the system. Till now we have not paid pretty much attention on deciding whether the system would be stable or not when subjected to a given input to the system. So, we will focus on this particular topic in this lecture. So, what we have in front of us is a system in state space domain. Okay. So, imagine that I have a autonomous system which is described in state space domain given as dx under bar by dt is equal to a double under bar x, right. So, this is an nth order system, nth order autonomous system, and we spend a lot of time to understand how to assess the stability of the system apart from the dynamical features of the system. And how would you decide on the stability of the system? Well, you know that the general solution of this system is given as x under bar of t is equal to summation I is equal to 1 to capital N C I e to the power lambda I t times the corresponding eigenvector V I. Okay. So, what you basically do is you list out all the eigenvalues, and what are the two major categories in which the eigenvalues may fall. They may either be real or they may be complex. Okay. And depending upon whether they are all real or complex, you can immediately see the eigenvalues and comment upon the stability. So, when the real eigenvalues are such that you have all negative, every single eigenvalue is negative, then you definitely say that the system is stable, which means every single state which the system can sample would be bounded, no state will blow up to infinity. This is the simple definition of stability, and otherwise the system would be unstable. Even if there is one eigenvalue which is positive, then e to the power positive quantity would blow up to infinity as t tends to infinity. Fine. And when you have complex eigenvalues, then you wanted to look at the real parts, and if the real parts, all the real parts are less than 0, and let me emphasize, all real parts are less than 0 negative, the system was stable, and otherwise the system was unstable, right. So, this was what you could infer from the state space domain analysis. You looked at the eigenvalues, every single negative eigenvalue, or in case of complex eigenvalues, every single real part being negative is the assurance of stability, and if even one of these is not satisfied, the system is going to be unstable. Pretty straightforward. Now, you have an input output type system where you would like to know the response of a system subject to a given input, and then now you have to define stability. So, you need to define stability, and we know that we need to do this analysis in the transform domain. So, let us see how do we do that. So, the first thing which you need to do is you need to define what exactly is the meaning of stability. Okay. So, if in response to a bounded input, so the first thing which you need to worry about is bounded input. What is the meaning of bounded input? There is a minimum and maximum which has been defined for the input. Okay. So, there is a minimum and maximum which is defined for the input. Okay. So, if in response to a bounded input the dynamic output of the system remains bounded, which means the response also is bounded between maximum and minimum, then the system is said to be stable, otherwise unstable. So, if we understand the meaning of bounded input, obviously the meaning of a bounded response would follow. So, let us try to understand the meaning of bounded input. Let us imagine a step input of magnitude A, right. So, what happens here in this particular case, you give your system. So, this is u of t and this is t. This the function is defined such that you have the value 0 and a value a at t is equal to 0, which is sustained there. Okay. So, this is 0, this is a. So, what is the input? What are the bounds on the input? Minimum is 0 and the maximum is a, right. So, there are bounds. So, therefore, a step input follows the condition of bounded input. A step input is a bounded input. What about a sinusoidal input, for example? Input. Okay. So, I have here t and I have here u of t is equal to a sin omega t. What is going to happen in this case? Your function is going to look like this, right. So, what is the maximum that you have? It is a, this is the maximum, and the minimum that you can have is minus a. So, again your input is bound between two limits, the upper one being plus a, the lower one being minus a. So, therefore, sinusoidal input also is an example of a bounded input. What about a ramp input? So, let me write here bounded, and I have a ramp input now. And what is the functional form of a ramp input? I have u of t is equal to a t, I will draw it versus t. You see here, the input goes to infinity as t tends to infinity. Okay. So, therefore, maximum is unbound. There is no upper cap on the maximum, and therefore, you have an unbounded input. So, therefore, you may not say anything or you may not be in a position to comment upon the stability of your system if you subject the system to a ramp input, but you may subject the system to a step input and you know that the maximum that my input or my forcing function can have is A, the minimum that it can have is 0. So, therefore, if my response also is bounded, then the system is called to be stable. Okay? Fine. So, now let us see how we can understand the dynamical behavior with respect to the stability of the system. The condition for stability is that a continuous system is stable if every pole associated with its transfer function is negative or has a negative real part. So, this means that I can simply look at the transfer function and say that I know that this system is going to be stable, or I know this system is going to be unstable. The way I used to look at the eigenvalues in the state space domain analysis, and the moment I used to see that the eigenvalues are positive, I used to say that the system is going to be unstable. When I saw all the eigenvalues to be negative, I used to say that the system is going to be stable. When the eigenvalues used to be complex numbers with all negative real parts, then I used to know that okay, the system will have oscillations, but oscillations will eventually die out, and when they had positive part, I used to know that there would be oscillations and the oscillations would increase in amplitude with time. The oscillations would sustain if you had a purely imaginary eigenvalue. So, similarly, now what I can do is I can look at the transfer function, the Laplace domain transfer function in case of continuous systems, and I would look into the poles of the system. Okay. And if every pole associated with the transfer function is either negative or the real part is negative, if it is a complex pole, then the system will be stable. Let us see if we can establish this. So, imagine that I have a PQ order system. Okay. So, let us take the most general case. So, I have G P Q of S, and what would this look like? This would look like A 0 plus A 1 S plus A 2 S squared up to A Q S to the power Q. This is the numerator having a polynomial of degree q divided by a polynomial of degree p. So, this would be 1 plus b s. So, b 1 s plus b 2 s squared plus up to b p s to the power p. Okay. So, this I am considering the most general case. Now, if this be the case, I would like to know the dynamical response, and the input itself has to be bounded. So, therefore, let us take the case of a step input. One thing which I have forgotten is that I need to multiply it with the static gain k. So, this is my general transfer function. So, therefore, what would be y of s bar would be transfer function multiplied by the Laplace transform of the step input. So, that would be a k 1 upon s multiplied by a 0 plus a 1 s plus a 2 s squared up to a q s to the power q divided by 1 plus b s b 1 s plus b 2 s squared up to b p s to the power p. How will I do the Laplace inversion? Well, I know that I will need to do a partial fraction. So, imagine that I can factorize the denominator. I do not worry about the numerator. I need to factorize the denominator, and let us say that the denominator can be factorized as follows. So, the numerator is simply a 0 plus a 1 s plus a 2 s squared up to a q s to the power q, and I have factorized my denominator into p number of factors. So, let us say the factors are s minus r 1, s minus r 2 up to s minus r p, right. What would be my next step? I will need to do a partial fraction. I will not worry about what exactly would be the form of the partial fraction, but I know what would be the functional form of the final partial fraction which I get, right. I hope you would agree that the final partial fraction would look like this: C 0 upon s plus C 1 upon s minus r 1 plus C 2 upon s minus r 2 up to plus C p upon s minus r p. There would be some numbers associated with C 0, C 1 and so on. I do not need to worry about that at this point of time, because they are not going to affect the stability of the system. They would affect the dynamics, but it will not affect the stability. We will see why. So, what is going to happen to y of t? So, now I will do a Laplace inversion. So, I will get y of t is equal to what? A k multiplied by C 0 upon s, and its Laplace inverse is simply C 0 plus C 1. Laplace inverse of this is not difficult, e to the power r 1 t plus C 2 e to the power r 2 t up to C p e to the power r p t. Fine. Now, you see the first term on the right hand side is a constant function, so it is always going to be bound, but rest every term on the right hand side has e to the power r I t, right. So, I have e to the power, what is the nature of e to the power plus r t. This is what? This is e to the power plus r t versus t. It looks like this, which means unbound, and e to the power minus r t, and in every case r is greater than 0. Okay. So, e to the power minus r t, you will have e to the power minus r t, again r greater than 0 versus t. This is bound. You can find the minimum maximum in that case. So, when r i's are real, when r i's are real, stability dictates that r i's must be less than 0 for y of t to be bound. If y of t has to be bound, then r i's have to be less than 0. You can see the graph on the right hand side. Now, the problem is when R I belong to complex numbers. When R I belong to complex numbers, then what happens? So, I have e to the power R I t, and let me write e to the power R I t as what? E to the power the modulus e to the power I theta, where theta is equal to tan inverse imaginary upon real, right. I can do this, fine. So, then what is going to happen in this case? Even before this happens, what I can do is I can simply write e to the power I t is equal to e to the power z 1 plus I z 2 times t, right. In this case, I do not need to even convert it to the r theta form. I simply convert it to r I is equal to z 1 plus I times z 2. So, this is what e to the power z 1 e to the power minus I z 2 t t, right. And now, it is very clear that this will give you oscillations, this will give you oscillations to your system, because those can be converted to sines and cosines, and this will give you decay or growth depending upon z 1. So, therefore, you will have decay for z 1 less than 0 and growth for z 1 greater than 0. Why? Because you have e to the power z 1 t, same thing which is there on the figure on the right hand side. Okay. So, therefore, it is pretty clear that when you have a system whose poles are all negative, or if the poles are complex numbers, all of the real parts are negative, it is only then that you can expect the system to be stable. Okay. So, let us quickly look into the statement which we had. A continuous system is stable if every pole associated with the transfer function has a negative real part or is itself negative. Okay. We looked into the transfer function for a first order system, and we got for the equation tau dy by dt plus y is equal to k times u. From here we got g of s is equal to k upon tau s plus 1. What was the response of such a system subjected to y of t and u of t as a function of t? If this is A, the response was bounded, and this was the response, right. What was the pole? R in this case was minus 1 over tau, which is less than 0. I encourage you to find this out, that for an equation of the form dy by dt minus y is equal to k u, for which g of s would be k upon tau s minus 1, your r will become 1 over tau, which is greater than 0. right. So, we had y of t is equal to a k 1 minus e to the power minus t by tau as the solution. If you follow the exact same procedure here, you will find that y of t would now become a k minus 1 plus e to the power t by tau. Okay. And what would this function look like? This function would look like this. This is y of t or u of t versus t. This is a, and what would the response look like? You can plot, the response looks like this. So, bounded and tau r was minus 1 over tau less than 0, unbounded r was 1 over tau which is greater than 0, as simple as that. So, you can simply look at the transfer function and comment upon the stability. Now, can we extend this to discrete system? Let us look and write down the general discrete time pulse transfer function. So, g of z would be what? G of z would be a 0 plus a 1 z inverse plus a 2 z inverse squared up to plus a q z inverse to the power q divided by 1 plus b 1 z inverse plus b 2 z inverse squared up to b p z inverse to the power minus p multiplied by k, the static gain. So, this is the general PQ order discrete time pulse transfer function. We will do the same analysis, subject this to a step input. What is going to happen? Y of z subject to a step input would be a k 1 upon 1 minus z inverse a 0 plus a 1 z inverse plus a 2 z inverse squared plus a q z to the power minus q divided by. Now, let me factorize the denominator. If you remember the lecture in which we introduced Z transforms, we can factorize the denominator now into p number of factors as this: 1 minus r 1 Z inverse, 1 minus r 2 Z inverse up to plus multiplied by 1 minus r p Z inverse. This is the way we will do the factorization. Then what we will do? Same, we will do a partial fraction. So, what is going to happen? This will be a k multiplied by c 0 upon 1 minus z inverse plus c 1 upon 1 minus r 1 z inverse plus c 2 upon 1 minus r 2 z inverse up to plus c p upon 1 minus r p z inverse. And therefore, y of n t, the inverse Z transform, will give me what? A k times C 0, because 1 over Z inverse is simply the Z transform of a step function, unit step function, plus C 1, we will take the inverse Laplace, and this would be e to the power n ln r 1. Please refer to our previous lecture, you will get this. plus C 2 e to the power n ln r 2 up to plus C p e to the power n ln r p. Fine. So, the first term on the right hand side is bounded because C 0 is a constant. Now, every term rest of the terms have e to the power n ln r I, right. In general r I may be complex. So, therefore, let me write this as e to the power n ln the modulus of r e to the power I theta, okay. And therefore, this would result in e to the power n e to the power I theta, simply I theta, I theta e to the power ln modulus of r. Okay. So, now what we see here is that we have e which is raised to the power ln r, and what is ln r? R modulus is z 1 squared plus z 2 squared root over, right. So, if I draw a plane in which I have z 1 the real part on x axis and z 2 the imaginary part on the y axis, then I have a unit circle, okay. And then for e to the power ln r to be less than 1 to be less than sorry, for ln r, not e to the power ln r, for ln r for ln r to be less than 0, you need r to be less than 1, right. The log of quantity less than 1 is negative. So, therefore, in this region, as long as you have z 1 z 2 in this region, your system is stable, otherwise the system is unstable, and I can draw a corresponding plot. So, this is for discrete, and what will be the corresponding plot for continuous? You have z 1, you have z 2, all of this has the real part which is less than 0. So, therefore, you have system which is stable here. So, you can always draw the complex plane and locate the poles there. For the case of continuous systems, the poles lie on the second and third quadrant, the system would be stable. For the case of a continuous system, you draw a circle of unit length, and if the pole lies inside it or even on it, you will have stability, otherwise you will not have stability. So, this is not this is what we had to study, which we had planned on studying. We started with the analysis of the systems in transform domain, studied everything about the continuous domain analysis, then we went to the discrete time domain analysis. We studied the effect of the form of transfer functions on the dynamical features, the speed of dynamics basically, and today we also looked into the effect of the features of the transfer function on the stability of the system. in the next lecture, which would be the final lecture, we will recapitulate everything which we studied in this particular course, and for today we will stop here. We meet again for the last lecture tomorrow. Till then, goodbye.